look at Friedel-Crafts reaction. Okay, recalling what we just learned about carbocation rearrangements for Friedel-Crafts acylations, let's consider how we could possibly synthesize the following. Here's a substitute, an alkyl substituted benzene that has an isobutyl group. Now, why does that matter to you? Well, probably most of you know what Advil, Motrin, or in the generic term, the chemical term, ibuprofen is. Ibuprofen is a pain reliever, particularly a specific class of NSAIDs, NSAID, non-steroidal anti-inflammatory drugs that are very effective. They're terrific. I take ibuprofen or its cousin naproxen routinely for pain issues. But by the Friedel-Crafts acylation, we can synthesize this. By the alkylation, we would have a problem, right? If we were going to take this apart based on the Friedel-Crafts alkylation that we had just done, we would have benzene and this alkyl chloride. Of course, what's the immediate problem that you recognize? If we were to try to do the forward reaction for this, we have a tertiary position next to the primary. So when we try to activate this, of course, we would get a hydride shift, essentially instantaneously from the synthetic point of view. That would give us the tertiary carbocation, and so we would get as a product the T-butyl group instead of the isobutyl group. And then of course what happens with alkyl substituent, this is actually more reactive than benzene. Now there are ways we could try and control that by having large excesses of benzene, but this can actually react again. And by way of this, I want to illustrate the other challenge with the Friedel-Crafts alkylation. This is over alkylation. So this is another problem with the Friedel-Crafts alkylation. Now, how does the Friedel-Crafts acylation solve this problem? Now remember, the T-butyl benzene is more reactive than benzene itself. So in the acylation reaction, and here's the general reaction, we have an acyl group. Now this is very different. Same reaction conditions, AlCl3, and we get only monosubstituted product with the ketone next to the ring. Now, think about the reactivity of this product. Is this product more reactive or less reactive than benzene? What do you think? Well, a carbonyl is an electron withdrawing group. It's a meta director, and so this is a deactivating group. So once we have the carbonyl on one time, then it's much more difficult to put the second carbonyl group on, so we can achieve selectivity in these systems. So this compound doesn't have the overalkylation product, and because of the carbonyl, and we'll see the cationic intermediate that's formed in just a minute, It doesn't have rearrangement issues either, and will allow us to install an isobutyl group. So, what's the general mechanism of this reaction? Well, first, there are two places where we have a Lewis base in an acyl chloride. The one that's, it's not that the oxygen can't act as a Lewis base and coordinate to the aluminum, but the one that's productive for us involves the chlorine coordinating. This gives us a Lewis acid, Lewis base adduct. Again, we can write a formal minus and formal plus charge here. Now, that oxygen has two lone pairs, and when the lone pair can come down and kick out the chloride, and produce an acylation ion. And of course the counter ion here is as before, AlCl4 minus. Now this acylation ion, I want you to notice the difference. Every atom in this, and that should be a plus, not a minus, in this acylation ion has an octet of electrons. Remember in our carbocation that we looked at a minute ago, it does not have an octet of electrons, and that's what contributes to the rearrangement to put the cation at the tertiary carbon instead of the primary carbon. This does not rearrange, but it is still a very good electrophile, and so then it will react with the benzene as we saw before. Now this carbon, if we look at it carefully, 1, 2, 3, 4 bonds, 8 electrons. So when my nucleophile attacks my electrophile, nucleophile, electrophile, be able to identify those pairs. When that happens, we need the carbon to lose 2 electrons. This then gives us an intermediate. Now I'm drawing in all the lone pairs for you. We made a carbon-carbon bond, and let me change that color so we see the bond that's made right there. We have a carbocation that's in the ring. Again, it's stabilized by resonance. This is a pentadienyl cation. 1, 2, 3, 4, 5 penta. 5 carbons, diene, 1, 2, and it's conjugated with the carbocation, pentadienyl cation. Now we just need our Lewis base, and remember this will have some AlCl4. I'll use that one specifically here. And I like to push arrows from lone pairs, not anions, at least at first, but we'll take some shortcuts later once we've mastered things. And then the carbon-hydrogen pair of electrons come down here, and this then gives us the Friedel-Crafts acylation product. Okay, now, how does this help us solve the problem we were dealing with a few minutes ago? Well, if here R, we're going to define it like this. What if R equals this group, the isobutyl group? Okay, that would then give us See how easy it is to make a mistake? Always look back and double check yourself. That gives us this isopropyl carbonyl substituent. Do you see? 1, 2, 3, 4 carbons. 1, 2, 3, 4 carbons. So how do we get from here to here? Well, do you remember that reaction we learned about the benzylic position? If we treat this carbonyl under the right conditions, and what were those conditions? Do you recall? Stop the video and see if you can recall it. Can you predict the reagents that we would use here? Remember, that's one of the ways that we need to be able to predict reactions, is what is the correct reagent? Hopefully you would come up with something like this: palladium on carbon and hydrogen gas. And so that's what we will use, palladium on carbon and hydrogen gas, and that converts a benzylic, remember, the carbonyl has to be at the benzylic position, converts it to the CH2 group. So for instance, this might be a way we could make an isobutyl group in ibuprofen, and of course ibuprofen is made on the kilotons scale annually, and it's made very efficiently, both synthetically and cost effectively. All right, so that's the Friedel-Crafts acylation. It solves those problems of overalkylation and carbocation rearrangement, but the Friedel-Crafts acylation has the same limitations, okay, as the alkylation chemistry. That is, the substituent cannot be an strongly electron withdrawing group. Remember, something like ammonium, that's a meta-directing deactivator group, nor can it be the amines, because they have a lone pair. That lone pair interacts with the Lewis acid, and that Lewis acid-Lewis base reaction is the fastest. Okay, so that's a little bit about scope and limitations of the Friedel-Crafts acylation. It solves some of the problems, but of course not all of the problems of the Friedel-Crafts alkylation chemistry.